Okay, today we're going to discuss the topic, machine learning is a tool, not a dogma, so that we can clarify. And this has to do with what idea do we know about machine learning? You know, every system has their own building blocks and their basic principles upon which whatever you want to do will be revolving around those, we call them fundamental principles. So which must always be noted at any point in time. Otherwise, very basic mistakes will be made that could lead to very fatal consequence or huge negative consequence. So that is why we have chosen to clarify this point, that when we say machine learning is a tool, just like any other tool, it could be successful, it could fail. It's not a dogma. A dogma is something that is fixed, that it never changes. This is what it's going to be. Nothing can change it. However, machine learning is not a tool, but we've seen people talk about machine learning as if they are dogma. No. For example, you use a particular machine learning algorithm. It could be in terms of algorithms. It could also be in terms of platforms that we're using. So, for example, we say, okay, neural network is very popular. So neural network is the best machine learning algorithm. That single statement actually could be clarified as a fallacy, because sometimes you may have neural network as popular as it is not performing in some function or on some data sets. Or let's take our popular support vector machine. It has been adjudged to be one of the very unique machine learning algorithms. But despite this, me saying that support vector machine is the best machine learning algorithm render that statement false, actually. Because it's like you are saying that machine learning tool, as far as support vector machine is concerned, is a dogma. This is the best algorithm to be used in all situations. No, it is not correct. There's nothing like that. You see? So the same thing goes for even when we talk of platforms. Which platform is better for machine learning? It's a function of what you want to do. What is the requirement of your organization? We have R environment, we have MATLAB environment, we have Python environment, we have the classical Weka environment, and so many environments that we are going to see that are available where you can implement your machine learning. So it is very important to get this part very right and correctly, so that when we are working on machine learning, we will be very careful and let some basic guidelines or principle guides the choice of algorithms we are going to use, rather than choosing it as if, oh, this is the best that can happen. You'll be so surprised that the best on the data set might not even get near might not even achieve 50% of what you are actually expecting. So this is why we always say, we mentioned it severally, we said, let the data speak. Let the data speak. The data actually let the data speak. We tell us which direction you should actually follow. So you have a data set, you put it on algorithm A, data set, maybe you have data set 1, data set number 1, we have data set 2. They could be from the same area or different area, it doesn't matter. So we have SVM, we have ANN. So SVM AI achieving maybe 99% accuracy, while this one is achieving like maybe 89. Then you have data set 2, SVM is still there, ANN. You might be surprised ANN might have 98% and SVM comes down to, let me say, 75% accuracy. It's a possibility. So it depends on the data set you are using. Also, it depends on the ability to carry out what we call the carefully selected hyperparameter optimization. This is very important. See, very important. So it's not the algorithm alone that can perform the unique magic, as you might call it. However, what's the effort of the one that is developing those models? This is very important. So in this sense, it is always very important to take note of these, of some very basic concept whenever we want to develop machine learning algorithms. So I said what to remember about ML models or classifiers, the case may be. As we may know, so machine learning algorithms, they are tools, not dogma. That is not something that you can just keep reciting, keep mentioning. No, this is the best, this will work for you. No, you have to see, check out, let your data speak. In fact, that's the statement I've seen today that is always true in machine learning. Let the data speak. You see, the data will tell us how you should manage the data or what you can get out of the data. So let the data speak, like I said, has been the statement that has come to stay, always very true when it comes to machine learning. Because sometimes when you apply your data set, when you apply an algorithm to a particular data set, you'll be surprised the kind of outcome you're going to get. So meanwhile, in another scenario, another data set, totally different, the same algorithm might not perform. So this is why we say it's not a dogma. Machine learning algorithms, they are tools. And tools could fail depending on the condition you subject the tools to. But in machine learning or data mining applications, data set has proven to be one of the very important conditions that can affect the performance of our algorithms. So if the data is very dirty, it's not clean, there are a lot of uncertainties in the data, this could go a long way to render your algorithm, no matter the power of the algorithm, to be ineffective. So if you don't carry out the appropriate pre-processing to be done, most importantly, the hyperparameter selection, you need to be very careful with this. This is very, very important. So that's why we say that machine learning algorithms, they are tools, they are not dogmas. We have to take note of that. Very important. There's no algorithm that's always better. So no classifier or algorithm is inherently better than any other. You need to make assumptions to generalize. That is, you have to make sure that, okay, what are the hyperparameters? Hyperparameter. These are the parameters that affect the performance of your algorithm. For example, if you're using super vector machine, you'll be talking of the C, the parameter C. You are going to talk about the kernel, polynomial, Gaussian, which of the kernel. Or we are talking of our very simple one, our friend, the k nearest neighbor, KNN. I'm going to talk about the value of k. Is k equal to 1? Our nearest neighbor, is it 1, 2, 3, 4? What is the value? What is the optimal value that works for you for that particular data set? It means you need to carry out carefully. You have to carefully select the hyperparameter value to be used. Also, what is going to be the distance measure that you are going to use? Is it the Manhattan distance, the shape distance, or Euclidean distance, or any other distance measure that you want to use? These are the two hyperparameters that are very, very important when it comes to k nearest neighbor. The number of k, the number of neighbors, and also the distance measure. So you have to select it. So if someone is using the so-called best algorithms, let's say you assume algorithm A is better in most cases because of your experience, then you have a new data set, and then you decided to use that same algorithm, but you didn't take care of try to select the appropriate the appropriate hyperparameter values to be used. You'll be surprised that you might end up having very bad results. So that is why it's not just enough to say that, oh, this algorithm is better than the other algorithm. No, we have to do the right thing. So the next thing to take note of, I said, is we need to say there's no classifier or model that is inherently better than any other. So you need to make assumption to generalize. So make sure you should do the right thing. And that is why the experience of the one developing the model is very important. That was why when we compare modeling, machine learning modeling to a kind of farming, you need the farmer that understands the appropriate time, which type of fertilizer to use, which kind of plant, kind of seed to plant, the amount of water to be used to water it at the appropriate, and the timing of the planting is very important. This is why experience counts or matters when you are trying to build machine learning models. Now, Another very popular, another example and another advice in this sense or principle or fundamental principle to take note is that we should try to start with simple classifier first. That is, start with simple algorithms. So when you have a new data set, try to see what can we get from KNN, for example. K-nearest neighbor, we have described it. You can refer to our videos on our YouTube for explanation of that. It's one of the very simple and easy to use algorithm. It could also be decision tree. Decision tree. Start for very simple algorithms and then see what you can get. Then before you start going towards complicated ones. Because these days we've seen people that just getting a data set, the next thing they think of is deep learning. No, everything is not for deep learning. Because everybody's talking of deep learning, doesn't mean you need to use deep learning to solve all problems. No, deep learning has its own strong points, especially when your data set is all about imaging, video, or text. However, if you have data set that is made up of numbers, simple numerical based attributes, then you don't need to go for deep learning. A very simple machine learning algorithm will do that for you. So that is why we don't need to assume that a couple of people, anytime they have any problem, the next thing is deep learning. No, you have to try from simple algorithm or classifier, and then you move up the ladder as you go. See? So rather than believing that the algorithm can always do the wonder, this is always the best algorithm, it's better to have smart features and simple classifier than simple features and smart classifiers. That is, to have a very simple algorithms with smart feature. That is, your feature also is very important. What is feature? Those are the attributes of your data set, which take us back to let the data speak that we mentioned. See, let the data speak. This is by far the most important statement I've personally come to know about machine learning, that let the data speak. The quality of your data will go a long way to determine the outcome of your experiment. And that's why you have to pay attention to your data set. So if you have smart feature, that is feature that can actually represent the area or the problem you are modeling, this is very, very important than just coming up with random data that are not even relevant to the problem you are solving. And then you want the algorithm to perform the magic to get excellent results. Things don't work this way. But sometimes you don't have control over the data set. This is what your client has. Then you have to try to say, okay, start from this simple classifier, and then gradually you can move towards more sophisticated or complicated classifier to see which one will do the work for you. So use increasingly powerful classifier with more training data, which we call bias variance trade-offs. So we've explained those also in our earlier videos. So sometimes once you have more data sets, then you can try going towards more sophisticated algorithms and then see if it's going to work for you. But if your data set is really very small, I can assure you, you are likely going to get better results using simpler algorithm than more complicated algorithm. But as the data increases, then the power of the simple algorithm might not be able to up to the task of modeling the entire system of data. But that is when the data is really big. And which data is enough, which data is big, I told us, is a relative term. So, and depending on the area you are actually modeling, in some area, very few samples can work. And in some area, you really need to have sizable number of data set. And of course, it depends also on the background of the data set. Is the data well collected? Is it clean? Is it having a lot of noise that you need to clean, and also for other things to be done? Again, it comes back to the experience. So that is why when we are building models, then we run into trouble. We try to seek for opinion or suggestion or guidance of people who have been working in this area before, so that you don't miss the opportunity. Sometimes you think that, oh, I've spent a lot of weeks on this, it's not gonna work. No, don't give up. Just a little question of guideline from someone who is more experienced might actually be what you need to get your problem solved quickly. And it has happened in several cases, whereby you're just missing a very simple step that you should have tried. So feature selection, try to normalize your data set. If the data set looks totally different, one attribute is having a very different, a big difference in range of one attribute to the other, then we try to, okay, can you do normalization? Maybe this could help your data set so that your algorithm will be able to generalize accordingly. Now, just as we say that algorithms, that or machine learning is not a dogma in the sense that there's no algorithm that you can stick to say, oh, we are going to be using this algorithm always because it's good. You might be disappointed because at some point in time, it might not work for you. Now, yeah, as we've mentioned also earlier, so by now you can know the difference. What is different between algorithms and their model? You see, model. You see, algorithm, these are the building block of machine learning. Why? It is when you apply the data, you provide your data plus algorithm plus data in the appropriate manner and the appropriate form, will lead to what we call model. This is what we call it machine learning modeling. So when your data plus your chosen algorithm, when you mix them together, the algorithm work on the data, the end result is going to be a model. If it is for classification problem, we call it classifier. It's good to clarify this. If it is for classification problem, then we call it classifier. Classifier. Because we use it to classify into A or B or A, B, C, depending on the number of classes you are having. Now, and this is the generic flow of it. You have your data, you have the feature engineering as the case may be, then you have the data modeling, which is actually using algorithm on your data that you already supply from the beginning. So when you do that appropriately, then you are generating model. The end result of algorithm and data modeling is a model, a machine learning model that will be generated. We check the performance measure. Is it okay? If it's not okay, we might need to go back here, just a step backward to change, maybe change the hyperparameter. Maybe the hyperparameter is not well selected. Check the values. So what is the value of K? Do I need to do better? Or sometimes it might not be issue of hyperparameter. It might be that you need to change the algorithm. Maybe K nearest neighbor is not working. Okay, try decision tree, it's not working. Okay, try support vector machine. Try neural network. Keep trying. Sometimes none of them is working. Okay, maybe you need to come and try ensemble, where we're going to mix them together. SVM, K nearest neighbor, decision tree, and so many other algorithms. Let them jointly decide what is going to be the outcome of this predictive solution or the task you want to estimate. So we already discussed ensemble enough. That's so many, you can refer to some of our videos in the archive on how to build ensemble. Sometimes ensemble might be what you need. And it's perfectly in line with the principle of let the data speak. Let the data speak. Sometimes what the data is saying might be too complicated for a single algorithm to detect. So in this sense, you allow multiple algorithms to listen to the data because the data do speaks, by the way. Yeah. However, our algorithm understand the language of the data, but sometimes they are not able to understand everything the data is communicating. They miss some of them. So when you use multiple algorithms, if one misses one, then another one will not miss that one. See? So at the end of the day, you have multiple algorithms coming together to solve your problem. You can actually achieve 100%. We've demonstrated it also for us, whereby you have an algorithm A, another one B, another one C, another one D. This one was able to achieve 75%. This one was able to achieve 74% accuracy. This one is achieving like 77% accuracy, and this one is 72% accuracy. However, when we merge the three of them together, the four of them together, or they could be five. If you are going to do voting ensemble, it's good to have like odd numbers so that they can vote. Majority vote which takes place. That is one type of ensemble. So let's say we have five of them, and this one is having 75% accuracy. By the time you allow these five of them to come together to decide, to model your data, we end up having 100%. which is far away from what individual were able to get. That is the power you can get from ensemble. However, as ensemble is, you can't just say everything has to go to ensemble. No, sometimes it's just a waste of time, because to develop ensemble system, you're going to spend a lot of time on it. But if a simple algorithm can do it, then why you need to kill a fly with a sledgehammer? That is what some people do sometimes. No, you don't need to do that. So you start from simple algorithm. If they fail, you try another one that may be better, and you keep trying until, okay, if nothing is working, then we can try to move to ensemble or whichever method or hybrid, as the case may be. Now, and then when you change the algorithm up to the point of using ensemble, maybe something might not get improved as you want. You might need to go back to feature engineering. Maybe we need to combine features together. Maybe we need to do some manipulation of some features. Maybe we need to even add more features. As the case may be, we may have to go back to the data preparation. So this kind of recursive procedure is usually encountered throughout the life cycle of machine learning development. So we have to pay attention to this. So it's not a single algorithm is going to solve our problem. No, this is why the topic of this talk is machine learning is a tool. It's not a dogma. A tool can fail at any point in time, but dogma is something that is fixed. It doesn't change. Wherever you take it to, it's the same thing you're going to meet it. So machine learning is not such. And the same thing goes to when we talk of tools and platforms. On which platform can we run our machine learning algorithms? You see, it depends on what you have the capability for, or what your company or your client wants you to use. Then in that case, you have to spend energy to see how you can use it there. We have so many outside there. You can see them there. You have the Python, we have R. There are some people believe in R so much. Everything they do is R. See, there's a platform for that. That's okay for them. But to say that if you don't use R, you cannot do machine learning, no, this is fallacy. This is not correct. The same to go to for Python. Python is very popular because a lot of people use it and a lot of freewares here and there. But still, that doesn't mean you're going to get accurate results in Python compared to R. No. Machine learning is not a dogma. So saying that you're going to get accurate results in Python always compared to other platforms, no, that is taking machine learning to become a dogma. No, it's not like that. So it depends on how the implementation of that particular algorithm has been done in Python. So which kind of equation has been used to write that particular code? The same thing goes to R. Somebody might want to also implement in MATLAB. See, a lot of people used to work in MATLAB before the advent of Python, R, and other programming languages, and they still stick to that. That doesn't mean that their code is going to be deficient or their machine learning model is going to be deficient. And some people also choose to use Weka for their own implementation, especially if you are not a programmer, because machine learning is not the same thing as programming. No, they are two different things entirely. You can do machine learning without knowing how to program. In the past, people used to think that if you don't know programming, you cannot do machine learning, because most online courses, the first thing they start teaching you is how to program in Python. I see this as a kind of, it's a kind of a way of unknowingly or indirectly making people to be disinterested in machine learning. Everybody can learn machine learning. You can use machine learning for your work even without writing a single code. And that is why these days now, a lot of systems, a lot of platforms, even universities are trying to promote what they call codeless machine learning. That is, you don't need to write any code. You can drag and drop, and you can build a very powerful machine learning analytic solutions. So, and that's the reality of the whole system. So either you want to use MATLAB, you want to use Weka, it depends on what procedure have you actually gone through to develop your model. That will go a long way to determine the accuracy of your work, not the platform. If you develop your code using Python, but you did a very, very quick, shady job, you didn't do a thorough job, you might have very bad accuracy. Let's say you didn't spend your time to do what we call hyperparameter hyperparameter optimization. In that case, you're going to get very poor results, because without hyperparameter optimization, how do you know which kind of value of that hyperparameter is going to work for you? So irrespective of the platform, if someone decides to do it in MATLAB and follow the appropriate procedure, check the hyperparameter, make sure everything is fine, you'll get better results. So it is what you give into it, your pre-processing steps. Is your data in need of normalization? Do you do normalization? You see, then the hyperparameter optimization. Once you have done the appropriate steps, the platform is irrelevant, by the way. So any platform can work for you, and you choose what you are comfortable with. This is machine learning. And that's why we say machine learning is not a dogma, it is a tool. And you can use it on any platform that you are comfortable with. Python, MATLAB, R, Weka, and so many platforms these days are available. C++, Java, there's so many platforms you can use machine learning from. So wherever platform you are comfortable with is immaterial. What matters is you need to make sure you follow the appropriate procedures that we have been describing for ourselves. So, and every platform, for example, Weka doesn't support deep learning before, but recently now they added deep learning. So you can actually do deep learning even from Weka. It means even without writing any program, any code, someone can use deep learning to solve problems. That is the level people are taking machine learning to. So they want everyone to be able to use machine learning, even if you don't have a background in coding. However, if you are good in coding, you are good to go for any platform that is comfortable for you. So this is another area. In addition to, there's no dogma when it comes to algorithms. There's also no dogma when it comes to which platform is better. It depends on the procedure. How are you able to follow the appropriate procedure in the right way and in the way it should be? This is what will determine to a long way the outcome of your modeling, most especially since we are dealing with the principle of let the data speak. So in that case, the data set vis-a-vis the procedure you have taken, we go a long way to really determine what is going to be the outcome of your modeling, not the algorithm only, and not the platform that actually you are using. Because there is no algorithm that is inherently better, but rather you need to make effort to make sure that you have passed through the necessary and appropriate procedure to be able to achieve the best possible outcome for your experiment. So hopefully this short discussion clarifies the idea of machine learning is a tool, not a dogma. Thank you very much for listening. And then we're going to take a couple of questions. And thank you for listening. Thank you.